In the previous class, we were looking at a worked example and if you remember we were looking at a case where the exit pressure PE was given to be 500 kilopascal and based on the other conditions, if you remember, the stagnation pressure P01 was given to be 1 megapascal and the stagnation temperature was given to be 500 Kelvin and A exit over A throat was given to be 3.5 and we established that for this value of back pressure there is a normal shock in the diverging portion. In the diverging portion of the nozzle. So, what we need to do is determine the flow properties at the exit of the nozzle. That was what we were about to do. Now, if I look at the flow situation, so this is station 1. This is the throat section. Remember, in this case the Mach number here has become equal to 1. So, the throat section also happens to be at the sonic state. There is a normal shock here and this is the exit of the nozzle. P exit is known is 500 kilopascal. Now, if I write an expression for mass flow rate through two sections, let us say the throat section and the exit section, I can write like this: m dot is equal to rho star u star a star or A throat. Remember, m is equal to 1 here, so A throat is equal to A star, and this can be written as rho exit, u exit and A exit. So, if I rearrange this expression, I can write this as P star over R times T star, and U star can be written as square root of gamma R T star because m is equal to 1, and remember A star is equal to A throat. So, I am explicitly indicating that here and this can be written as PE over R times TE, and this can be written as ME times square root of gamma R TE, and this is AE. Now, if I rearrange this expression slightly, notice that I can cancel out these terms here, and if I write this as P star over P01 times P01 over P exit, notice that I have taken the P exit to the denominator here. The square root of gamma R also cancels out from these two, and I can write this as remember there is a square root of T star here, there is a square root of T star here. So, I can actually write this as square root of T0 over T star. So, I multiply both sides with the square root of T0. So, let me write this as A throat divided by A exit is equal to, so ME is still left on the right hand side, the A exit has been taken here, and I have a square root of T naught here. So, I can write this as square root of T naught over TE. Okay. Notice that I have multiplied both sides of the equation by a square root of T naught to write the expression in this way. Okay. T naught over T star is known, that is nothing but gamma plus 1 over 2. P star over P01 is also known, that is an isentropic flow. I can get this value from the table. Notice that P01 over PE is also known. This is P01, not P02. I do not know the stagnation pressure downstream of the shock wave because I do not know where the shock wave is. Until I know the Mach number upstream of the shock wave, I will not know the stagnation pressure downstream of the shock wave, but this is stagnation pressure upstream of the shock wave. This is P01, I have multiplied and divided by P01. So, this is known, this is known, this is known, and this is also known. Okay. Now T0 over TE I can write in terms of the Mach number at exit, so that means I am left with only one unknown, correct. So let us go ahead and do that and see what we get. So P star over P01 from the tables comes out to be 1 over 1.893, and P01 over P exit can be written as 1 megapascal is nothing but 1000 kilopascal divided by 500, and this is square root of 1.2, because it is gamma plus 1 over 2 times, we are also given that A exit over A throat is 3.5, so this is 1 over 3.5, and this can be written as M exit times square root of 1 plus gamma minus 1 over 2 times M exit square. So if you plug in and iterate, remember we are looking for a subsonic solution here. So I can solve for this equation for M exit and get M exit to be 0.2735. Okay, it is not very difficult to solve this equation. It is a simple quadratic equation. It is not very difficult to do that. So we take the subsonic solution, which is 0.2735. So from this I can get my T exit to be T exit over T naught times T naught. T naught remains the same across the shock wave also. So I can get this to be 1 over 1.015 times 500, which gives me 493 Kelvin. That is the static temperature at the exit. Static pressure at the exit is 500 kilopascal, that is already known, and stagnation pressure at the exit P0 exit can be calculated as P0 over PE times PE, and P0 over PE for this value of Mach number we can get from the tables. Right. For this value of Mach number I can get P0 over PE from the isentropic tables, and this comes out to be 1.056 times 500. So the exit pressure, the stagnation pressure at exit is 528 kilopascal. So at the inlet the stagnation pressure is 1000 kilopascal, and at the exit the stagnation pressure has reduced by almost 50%, nearly 50%. Okay. So there is a tremendous loss of stagnation pressure. So we will still go ahead. So this actually completes the requirements for the problem, but for the sake of completeness we will go ahead and try to determine where the shock is located. Okay, that is also very important in many applications. So let me denote the shock, the state ahead of the shock by X and the state downstream of the shock by Y. Now I know P0x over P0y, right. So P0y over P0x is nothing but 528 divided by 1000. So that is 0.528. From normal shock table, I can get mx to be 2.43. So I know the Mach number here as mx is 2.43. Remember this part of the flow is isentropic with A star equal to A throat. Right. So I can get, so from the isentropic tables, the A by A star where this M occurs comes out to be 2.4714. So that is the A by A star area ratio where the normal shock occurs. For comparison, you know that A exit over A throat is 3.5. Okay, so this occurs somewhere probably in the second half of the divergent portion of the nozzle. So that completes the problem entirely. Okay. It is also possible to solve this problem iteratively by assuming the shock to be located at some place. So you will do this the opposite way. You assume the shock to be at some A by A star, and then for that A by A star you determine your mx and then my, p0y, and then exit static pressure. See if the exit static pressure matches the 500 kilopascal. If it does not match, then you move the shock and then do this iteratively. It is possible to do it that way also. Okay. Any questions? Okay. The presence of the normal shock during the startup operation of a convergent divergent nozzle poses lots of problem during operation. If you remember, we said that unless the P0 over P ambient is more than 3, we would prefer to have a convergent nozzle and still live with the loss of thrust. Okay. The reason being, when you add a convergent divergent nozzle, the startup becomes very difficult because there is a normal shock which needs to be driven out. So there is a lot of loss during the startup, and so convergent divergent nozzle adds a lot of complexity to this. Okay. So it is avoided if the stagnation pressure P0 over P ambient is 3 or maybe even 4, it is not worth adding a CD nozzle. Now the startup difficulty that we saw with the convergent divergent nozzle is also seen in other devices, but it exhibits in a different way. Okay. One of the most important application is supersonic diffuser. A supersonic diffuser is typically used in ramjets, which are, for example, either engines that use pure ramjets, which would be missiles, or it can also be used in supersonic transport vehicles like a Concorde or maybe fighter aircraft, which use derivatives of the ramjet engine. So they have a turbojet and a ramjet option. In both these cases, when the flight Mach number exceeds say 2 or so, then the idea is to decelerate the air sufficiently so that you convert the momentum of the air into pressure. Okay. So then when you do that, we can completely dispense with the compressor. You do not need a compressor because the slowing down the air gives you the high pressure or the pressure rise that you want, and you no longer need a compressor to increase the pressure. Okay. But this deceleration has to be done very carefully in something called a supersonic diffuser. A supersonic diffuser is the exact opposite of a supersonic nozzle. Okay. If you remember, a supersonic nozzle under design operating condition, right, has m equal to 1 at throat. So we have a subsonic flow coming in, m becomes 1 at the throat, and we have a supersonic flow going out. So this is a nozzle. Now a supersonic diffuser acts in the exact opposite way. We take a supersonic flow, decelerate it so that we get a subsonic flow at the exit. And if you remember, the pressure decreases from here to here in the nozzle operation. So similarly in the diffuser operation, the static pressure would increase from here to here. That is the general idea. But because you have a normal shock during startup of these devices, you have a lot of difficulty realizing this in practice. This sounds very good on paper, but very difficult to realize in practice, and those are some of the things that we are going to look at now. Okay? So, a supersonic diffuser, for example, would perhaps look like this. There are many other variations of this. This is probably the simplest one. So, it takes a supersonic flow and decelerates it to a subsonic flow. This operates in the other direction, and there is an increase in pressure, static pressure, as you go from the free stream to this. Okay, so this is exposed to the free stream, so the air is coming in at a supersonic Mach number into the diffuser, and we are decelerating it. This is one of the applications. Okay. Now, a supersonic, so what we will do is we will actually work out a numerical example which illustrates this concept. Another application where you get into difficulty with the startup problem is the so called supersonic wind tunnel. Now, many times in aerodynamics and maybe even in propulsion, you need to test components and engines and other things in a supersonic stream. So, let us say we want to test something in a supersonic stream. Let us say that we generate a supersonic flow. So, let us say that this is my supersonic flow and I have a supersonic jet coming out. Okay, let us say that this is ambient pressure at 100 kPa. Now, if I design the nozzle, then under design operating condition, just for the sake of argument, let us say that the exit Mach number here is 3, and it is operating under design condition, so that the jet comes out like this. And so the jet is neither over expanded nor under expanded. So, you get a correctly expanded jet which looks like this, which is at a supersonic Mach number. So, I can insert a component into this and study the performance of the component under supersonic conditions. If I want to test it, let us say Mach 3, that is what I would do. Okay, this is correctly expanded. Now, if you actually think about this case, remember when we run a compressor, we talked about this also earlier, we use compressed air from storage tanks and where the air is stored from compressors. So, we need to spend energy to compress the air to a certain pressure before we can actually run it through this to get a jet like this, right. So, if you look at a situation like this, right, the static pressure, so if you look at this, the flow when it comes out at a Mach number of 3 and a static pressure of 100 kilopascal. Right, PE in this case is 100 kilopascal because it is correctly expanded. Right. So, if it is correctly expanded and ME is 3, if you go to your tables, I can get my P0 value for this case to be, what is it going to be? Let us go to the isentropic table, and if you go to the isentropic table, you get the value to be for Mach number 3. .73. So, P0 over PE is equal to 36.73 from isentropic tables. Which means that the compressor needs to generate or produce air at a pressure of 36.73 bar or atmosphere. Now, that is going to require a lot of energy to compress air to a stagnation pressure of 36.73 bars. So, we compress air to this pressure, put it in a storage tank and then connect the nozzle to the storage tank, everything works fine here. This is a lot of energy. We can actually improve upon this by doing the following. Let us say that instead of allowing it to expand into the atmosphere this way, we want the Mach number to be 3, that is our desired test section Mach number. Let us say that we do something like this. Right? So, same nozzle, same everything, but now instead of allowing the nozzle to exhaust to the ambient, let us say that we put a test section, we add walls to this. Okay, so this is ambient at 100 kPa, then we allow it to exhaust like this, and we design things so that there is a normal shock which stands here. So this is a normal shock. So the test section Mach number is ME equal to 3. So I still satisfy the requirements for the testing, but now I have put a test section, I have put walls around the test section. This is, remember, this is a free jet. This is a free jet which exhausts into the ambient. Now we have a test section where we have supersonic flow, right. So now I have a normal shock like this. So let us say that this is X and this is Y. This is a normal shock at Mach number 3, correct. So I can from this I can do the following. Notice that mx is equal to 3, right. Py, static pressure at the exit, is equal to 100 kPa. So if I go to the normal shock table, I can get Py over Px to be. So if I go to the normal shock table for m equal to 3, so from the normal shock table, for a shock that occurs at mx equal to 3, I get Py over Px to be 10.33. Okay. This means that my Px is, what is my Px? 100 kilopascal divided by 10.33. Approximately 10, correct? Approximately. If this is approximately 10, what is my P0x? Mach number is 3, so I can write P0x equal to from the isentropic table we get P0x over Px at m equal to 3 to be 36.73, that we have already seen, right. 36.73 times 10. Did I do this correctly? That is 10 kilopascal, correct? This is 36.73. Oh, this is 10 kilopascal. Yeah, that's correct. This is correct. So this is 3.673 bar, correct? 3.673 bar. Now you can see what normal shock compression is doing for you. So by adding a test section and a normal shock at the end of the test section, I have reduced my compressor power by how much? By a factor of 10. So the compressor power now has become 1/10 of what it was if it was a free jet, right. So that is what the normal shock compression does for you, because this pressure can be less and you are getting a substantial compression across this can be less, so that means the stagnation pressure can also be less, okay. In fact, I can make this even better if I add a diffuser to this. I can add a diffuser to this section like this, and if I diffuse the flow, then there is going to be another increase in pressure across this, which means this can operate at an even lower pressure. So there will be a marginal increase if I add a diffuser. So what I am trying to tell you is, if you want to test objects and other things in a supersonic tunnel, so this would become a test section. The entire setup is called a supersonic wind tunnel, okay. So you can see that adding a diffuser will actually benefit, and we can design things properly. If you design things properly, we can actually reduce the amount of power that is required. But the tunnel will usually have operating problems. The tunnel will usually have starting difficulties associated with the normal shock that we normally see. So a supersonic wind tunnel would actually look like this. So we have a convergent divergent nozzle, a test section like this, and we actually put a diffuser, which is what we talked about here, right, supersonic diffuser. So we have a supersonic nozzle, a test section followed by a diffuser, correct. So this is the So, this is the nozzle part, this is the test section, and this is the diffuser part. So, flow comes in, reaches the test section, supersonic Mach number, and then goes out like this. So, there is one throat here, notice that there is one throat here and another throat here. Okay. The idea is during operation the air comes in at a certain static pressure, goes through, becomes supersonic, and then if I am able to recover the momentum of the air and convert that to static pressure, I can feed this air back into the inlet here. Or I am sorry, if I recover this as the momentum, I can feed the air back into my storage tank, because I have now converted the momentum into high static pressure. So, I can put it into the storage tank and then use it back here, which means I can actually run this continuously with minimal energy input, not zero input, but minimal energy input. That is the whole idea of adding a supersonic diffuser like this. The supersonic diffuser would be very effective in, when it comes to converting the momentum of this high speed air into static pressure. Okay, that is why we add this diffuser. But now if you think about starting the tunnel, okay, initially everything is at atmospheric pressure, right? Everything is at atmospheric pressure. Let us say we start the tunnel and we go through the sequence that we described yesterday. Initially we establish a small flow here, subsonic here, accelerates slightly, again becomes subsonic, and then just goes through. Okay. So, we crank up the pressure. In this case we are not lowering the ambient pressure. Yesterday when we talked about this, we were looking at keeping the inlet stagnation pressure constant and then lowering the ambient pressure. Now we are actually running the compressor. So, we are actually increasing the stagnation pressure, keeping the ambient pressure the same, right. So, I increase the stagnation pressure a little bit more. I now set up a situation where the flow accelerates, m becomes equal to 1 here, right, and then again subsonic flow throughout, perhaps m becoming equal to 1 here maybe. Okay. Now, if I crank up the stagnation pressure a little bit more, what happens next? I have a normal shock, right, somewhere here. I set up a normal shock somewhere here, and once I set up a normal shock here, the mass flow rate that comes through this, right, the mass flow rate that comes through this part can be written like this, right, m dot nozzle can be written as P0 nozzle times A throat for the nozzle divided by square root of T0 nozzle, and then we have a quantity which depends on the only on the property of the gas. That will be remain the same because the same gas is going through both this. Remember, there is a square root of gamma over r, there is a big expression which is immaterial to our discussion. So, I am just going to leave that as it is. Okay. And remember, the stagnation temperature remains constant throughout, there is no change in the stagnation temperature. Now, assuming that the two throat areas are the same, so I get m equal to 1 here, so I am going to get m equal to 1 here also. So, that means the mass flow rate that goes through the diffuser is like this, right. So, the mass flow rate that goes through the diffuser can be written like this, m dot diffuser is equal to P0 diffuser A throat diffuser divided by square root of T0 diffuser, and then same thing. Now, if I compare these two expressions, okay, T0 is the same, so I need not worry about this. So, the quantity within this parenthesis is also the same, so I need not worry about that. Now, what can we say about P0 nozzle and P0 diffuser? Remember, there is a normal shock that is sitting here. P0 diffuser, there is a loss of stagnation pressure across the normal shock. So, P0 diffuser is less than P0 nozzle. If the throat areas are the same, and M is equal to 1 at the throat, then we can see that the diffuser is able to swallow a mass flow rate which is little bit less than what the nozzle is providing. The nozzle may be providing, let us say 1 kg per second or 10 kg per second, but the diffuser is able to swallow only 8 kg per second or 9 kg per second. So, what happens to the remaining mass? I am starting the tunnel, right? Remember the sequence that we are going through. We are starting the tunnel, cranking up the pressure, stagnation pressure, trying to push the flow through the nozzle so that we get a shock free flow with supersonic Mach number here, right. So, I have come up to a point where I have a normal shock here, and this is the situation that I am faced with. So, the diffuser is not able to swallow all the mass that I am pushing through the nozzle. If I do not do anything, right, then the pressure builds up here because of the accumulated mass. When the pressure builds up here, what does it do to the shock wave? Pushes the shock wave to the front. So, the shock wave can go only up to the throat, because once it reaches the throat, M is equal to 1, so the shock wave becomes an acoustic wave. It becomes, the strength becomes infinitesimally small. So, the tunnel becomes shock free. However, the stagnation pressure is high. We have artificially pushed the shock here. So, for a moment we have shock free flow with M may be equal to 1 here and subsonic flow throughout. But the stagnation pressure, we have cranked it up to a higher value. So, then that tries to push the flow again through this, and we again set up a normal shock here, and then the pressure builds up, again it goes back. So, the tunnel will never start, it will just keep oscillating like this, okay? It will just keep going back and forth. It will never start because this shock cannot be swallowed by the diffuser because of the mismatch in the mass flow rates, correct. So, this mismatch is happening because there is a loss of stagnation pressure across the shock wave. How do we get around this? One way of getting around this is to adjust the area of the throat area of the diffuser. Do not make them the same. If, for example, I increase slightly the throat area of the diffuser, then I am able to, the diffuser can swallow all the mass that this is supplying. So, which means when we are starting the tunnel, we need to slightly open this diffuser. So, the shock is here, and I figure out my P0 diffuser over P0 nozzle, and then I open up the diffuser by that much. Then what happens? The shock moves a little bit down, right. So, then the shock goes from here to here. As I keep cranking up the stagnation pressure, it moves down. So, what is the worst case scenario? What is the maximum opening that I have to provide for the diffuser? The maximum loss of stagnation pressure occurs when the normal shock stands in the supersonic test section, because that is where the Mach number is going to be the maximum. That is where the Mach number is the maximum, that is where this loss of stagnation pressure is maximum. So, that also tells me the maximum area to which I need to open this. So, if I open the diffuser to this area, then the starting shock very easily goes through and then locates itself somewhere here. During steady state operation, it will locate itself here. Notice that when the shock wave goes through, when the initial starting shock is swallowed by the diffuser, you cannot keep the throat area of the diffuser larger than the throat area of the nozzle. You have to reduce it back to the same value as the nozzle. For continuous shock free operation, the two have to be equal, but during startup, because of the normal shock and the loss of stagnation pressure across the normal shock, I open it to push the flow through and then I bring it back, right. That is what I do. And so, this starting shock with the supersonic, in a supersonic nozzle poses difficulties wherever it is used. Whether it is a nozzle or a diffuser, it creates problems wherever it is used. So, we need to make sure that we understand the dynamics of what happens here, so that we can handle this properly. So, opening the diffuser to accommodate the normal shock is one strategy, but that is also mechanically very complicated to implement, right. You need to have throat areas which are movable, that is not so easy to implement in a mechanical sense in practical devices. Another way of doing this is to provide, for example, openings like this, so that when a normal shock stands here, right, and there is a mismatch in mass flow rate between the two, right. So we have 10 kg per second coming through, only 9 kg per second going through here, right. So you provide these kinds of openings, so the remaining 1 kg per second can be bled off through this openings. So the flow can actually go through this. When you do this, there is no problem, there is no mismatch. 10 kg per second is coming through and 10 kg per second is going out. So there is no accumulation of mass, right. So the normal shock keeps moving, then eventually you close the opening so that the shock locates itself here and the tunnel is fully started. When we say the tunnel is fully started, what we mean by that is, when we say the tunnel is fully started, we mean two things: shock free and supersonic flow in the test section. Okay? So the starting process becomes somewhat complicated, but once you are able to handle this, you realize that the starting difficulty has to do with the mismatch of mass flow rate, which is why I said that this expression, when I wrote down this expression for the first time, I said this is one of the most important expressions in gas dynamics. Okay. Once you realize that the mismatch is because of the different stagnation pressure, we can work around this. This is actually a far more practical solution than changing the throat area. Although both are used, this is a far more practical solution. For example, the supersonic intake of the Concorde uses this strategy to spill the mass. So what we are doing here is spilling the mass, right. So we spill the mass around the tunnel to get the shock swallowed. So when you do this, the shock keeps moving down like this. As I crank up the stagnation pressure here, the shock keeps moving like this, it goes out. Excuse me? They are opening the walls of the test section, right? That's not providing leakages. No. This is controlled bleeding of the flow through the walls of the tunnel. We can actually provide passages like this to bleed the tunnel, and they are closed once the flow is established. You cannot keep them open all the time. You have to close them once the flow is completely established and the tunnel is started. Okay? This is a practically viable strategy which can be used.
Or we can push the shock by increasing P naught.
Push the shock where?
You
can't. That is what I said. If you keep the throat area the same, and you don't do the spilling, I come up to a certain P naught, so I have a shock here, right. Now there is a mismatch, so only 9 kg per second is going through, 10 kg per second is coming in. There is a 1 kg per second mass which is being accumulated. Even if I increase my pressure here, the shock cannot move downstream, because I am building up mass here continuously and there is an increase in pressure. So the brute force way of pushing the shock down here will not work because of the mismatch and loss of stagnation pressure across the normal shock. Okay? So when you do that, what will happen is this increase in pressure will tend to push the shock backwards. Then you establish shock free flow, but subsonic flow in the test section. Because this stagnation pressure is already high, again it will trigger a normal shock. It will try to push the flow through this, and again it builds up. So this will go in cycles. So you cannot push the shock through the system simply. The diffuser or the second throat has to swallow the shock. Okay? So that's why if you look at this terminology, swallowing the shock, because you are talking about mass flow rate, the second throat should swallow the starting shock. Okay? But I like to use the following example in this context. Let's say that mother is trying to feed the child. The food does not go in easily. What does the mother say? Open wide. You can't shove more food down the throat, the child is not eating, right. So that is exactly what is happening here. This is only capable of handling 9 kg per second. If you want it to handle more than that, what do? You open wide so that it can go through. Simply pushing down more mass flow rate here is not going to move the shock down here. That will not happen, right. You can provide these kinds of things to handle the starting shock. In fact, that is exactly what one of your classmates is doing. He is doing that, are you not? So that is a very viable strategy and it also works, okay. So the terminology also talks that way. We say that the nozzle is choked. That means that is the maximum it can handle. Then we say the starting shock has to be swallowed. This terminology actually, there is a certain meaning behind it. This is what we mean, okay. You increase the area to allow the increased mass flow rate to go through. What we will do now is a worked example which involves these types of ideas. How do we change the area to get the tunnel started, and then how do we bring it back for steady state operating conditions and so on, okay, for a supersonic diffuser. So we look at the next worked example. Which involves a supersonic diffuser. So we are looking at the following situation. So we have a converging diverging diffuser, and we have flow. So this is facing flow. Let us say it is designed for a free stream Mach number of. So this is the free stream which enters the nozzle. So we are supposed to decelerate it to a subsonic Mach number, okay. So design operating conditions is when the free stream Mach number is 2. So when the free stream Mach number is 2, the flow is completely shock free, and it goes from a supersonic Mach number to a subsonic Mach number, with the Mach number at the throat being equal to 1, okay. So terminology, this is called the inlet. Okay. So this is the inlet area and this is the throat, and this is the free stream. All free stream conditions will be denoted with the subscript m infinity. Now we are going to look at transient operation of this diffuser, what happens under design operating conditions and what happens when the operating Mach number is, let us say, below design value, which is let us say 1.5. So we will look at the operation for m infinity equal to 2, which is the design condition, and m infinity equal to 1.5, and see how things change. That is what we are going to do next. So under design operating condition, so when the inlet Mach number is equal to 2, from isentropic table we get A inlet over A throat design. is equal to 1.6875. The mass flow rate under design operating condition through the nozzle can be written like this: m dot design is equal to P0 infinity times A throat divided by square root of T0 infinity times this quantity gamma over R times 2 over gamma plus 1 to the power gamma plus 1 over gamma minus 1, square root of that. Now, I can rewrite all these quantities in terms of the static quantities under free stream condition. That is how it is usually done for supersonic intakes, because the aircraft may be flying at a certain altitude. So, we know the static temperature, we know the static pressure, and we know the speed, so from which we can calculate the Mach number. So, rather than use the stagnation conditions at free stream, it is conventional to use the static conditions at free stream, because they are known in this case. The aircraft or the missile flies at a certain altitude, so we know these quantities, right. So, from isentropic tables, isentropic table for m infinity equal to 2, I can retrieve the following quantities: P0 infinity over P infinity is equal to 7.82445 and T0 infinity over T infinity is equal to 1.8. So, if I plug in these values here, I get m dot for the design operating condition as 5.832 times P infinity A throat divided by square root of T infinity times gamma over R 2 over gamma plus 1 raised to the power gamma plus 1 over gamma minus 1, square root of that. So, if you think about the stream tube that enters, then we can actually sketch the stream tube that enters the intake like this. So, this much of the free stream enters the intake under design operating condition. Okay. In fact, this area over here is called the capture area. So, the intake may have certain geometric dimensions, but what is the cross sectional area of the stream tube that enters the intake? That is called the capture area of the intake. Okay. So, in this case, the capture area is the same as the, so for design operating condition A capture is the same as the inlet area for design operating condition, which itself is 1.6875 times the A throat. So, this can be written as 1.6875 times A throat. So, that A capture divided by A throat for design operating condition is 1.6875. So, these are for the design operating condition. What we will do in the next class is see how these quantities change when we change to an operating Mach number of 1.5. So, when m infinity instead of being 2, when m infinity becomes 1.5, how do these quantities change and how does the performance of the intake also change? That is what we are going to look at in the next class.